And we're back. Welcome back and happy Tuesday. Today, we will continue on with our discussion of neural networks with a focus on the development of the back-propagation learning algorithm. Where we last left off, we talked about layers of compositional functions through weighted sums. We had our inputs derived from the multi-layer perceptron, this idea of combining perceptrons, and we softened the hard threshold using the hyperbolic tangent, or tanh. And so with a series of layers, we call that a neural network. We start with our input layer on the left. We have our hidden layers in the middle, and then our output layer on the right-hand side. We also described a naming scheme where we name all of the weights associated with a particular layer, superscript L. Now, we had index I that indexes over the input nodes, which are outputs from layer L-1, but they're inputs to layer L. And that has the dimensionality, i.e. number of nodes, that are D superscript L-1. And then we also have the output nodes that are in layer L. They have their dimensionality, and index J references the particular node in layer L, the jth node, into which some number, D superscript L-1, many nodes from the input layer before it, feed into through a weight. And so we said when we compute the output in layer L for node J, X sub J superscript L, that's just our nonlinearity evaluated on the score for that node J in layer L, which is just the sum of all of the weights incident to node J in layer L times the input nodes, those weighted sums, going into from layer L-1 indexed by I. Okay, so that's our weighted sum. And so we said we take our input and feed it forward to the next layer, the next layer, the next layer, until we get, for a single output node for layer L, that's going to be our hypothesis, h of x. So let's take a look at our backpropagation algorithm. And so we have all of our weights. Collectively, these define the parameters for the neural network, and a particular instantiation of all these weights, Wij superscript L, are going to determine the particular hypothesis, h of x. And so if we look at our label instance pairs, xn, yn, the error on that example is the pointwise error evaluated on the hypothesis on that in-sample point, h of xn, the difference between that output for the hypothesis and the ground truth target function label. So we're going to call that E of W. And the reason why we call that E of W is because the error is dependent on the weights. If the weights determine the hypothesis, and the error is the difference between the hypothesis and the unknown target function's label on that input, well, a different choice of H, i.e. a different choice of W, is going to have a different error. So this error is a function of W. Change W, you change the error. Now, to implement stochastic gradient descent on our neural network, what we need then is the gradient of the error at the output, error with respect to your hypothesis and the unknown target function, with respect to each one of these parameters W, for all I, J, and L. So that's all inputs, all output nodes, and all layers. So that's going to be potentially a lot of calculation. Now, you can evaluate each one of these partial derivatives of the output error with respect to weight ij superscript L, each one of these weight vector parameters. You can do this one by one, either analytically, and when we say analytically, you're actually using the chain rule and finding that derivative successive layer after layer after layer. Because if you think about it, you have an output node through a weight to compose a score through that nonlinearity to an output node. And so you can compose this going backwards through chain rule for derivatives. Or you can do this numerically. Now, to evaluate this partial derivative of our output error with respect to each of these weights, numerically you take the weight and you change it a little bit. You wiggle it, you jiggle it, so to speak, numerically. And when you change it a little bit, you observe the change in error. That's effectively your derivative, your gradient, your partial derivative of the output error with respect to that weight vector. Because each weight vector, again, as we said, contributes to that error because they contribute to that hypothesis. And with the choice of hypothesis, our weight vector, the error changes. And so by changing this weight a little bit in value and observing how the error changes, that's how you can numerically do this. But it's a little bit of a mess. And the reason why it's a mess is because there's a lot of weights for which you have to do this. That's every weight for every layer, for every input, and every output node. And so more efficiently, we can use the structure of our neural network to make our computation more efficient. And so here we have a general scheme of the structure of our neural network. We have our output in some layer L-1 through a weight vector, defines or contributes to a score for node J in layer L. We pass that score through a nonlinearity to get an output for that node J in layer L. And so if we compute this error, we can compute this partial derivative error for the output with respect to a particular weight vector as taking the intermediate steps. There's a linkage functionally between the error at the output here and the score that you feed in through the nonlinearity, and that linkage is the nonlinearity. And so we can decompose, akin to chain rule, the error at the output with respect to weight vector. This weight vector is the error with respect to the score. Well, that's going to have to do with the nonlinearity, and we do that derivative, the partial derivative, times the partial derivative of the score with respect to the weight vector. That weight vector contributes to the score. And so we can put these all together via chain rule and get a more efficient computation for the same quantity without going through all the trouble of chasing individual chain rules down the neural network or wiggling each one of these weight vectors to find the commensurate change in error. So let's take a look at these terms here that we use to construct this partial of the output error with respect to the weight vector. This first term, the partial of the error with respect to the score, well, that's just having to do with our nonlinearity. And we're going to give that term a name. We're going to call that delta J, the delta of that particular jth node in layer L. Then this next term, the derivative, partial of the score at node J layer L with respect to weight vector ij superscript L, we're going to look at this network and we say, okay, how does the score change with respect to the weight vector? Now, of course, this weight vector, it is multiplied by this input, and you can think of that input as a constant. And if the variable of derivation is this weight vector w, well, that's just a constant times w to the 1 power. That's just our xi superscript L-1, the input from the ith node in layer L-1. Okay, so that's the rate of change of the score with respect to w. It's that constant. All right, so we have those two terms. So let's take a look at what this output might be for the final layer, which is h of x. And we want to compute this quantity, this delta, that's that partial of the error with respect to the score. And we're going to do this for the output layer. So for the final layer, the output layer, we said that index that describes the layer is going to be capital L. And we have a single node, so j is equal to 1. And this is assuming we just have a single output node. So we're going to write delta sub 1, because this dimensionality is 1, so it's only one node, delta sub 1 superscript big L. is the partial of the error as a function of W, the output error, with respect to the score S1 superscript L. So it's the score of node 1 in the else layer. Well, if we think about what the error at the output is, well, we have the output of the output node. That is X1, the output of that one node, the first node, there's only one of them in the output layer, superscript L, minus our ground truth label, yn, and assuming it's real valued, we take the square of that difference, the squared error loss. So that's going to be the error of the output. Now, of course, what does it mean to construct this output for the output layer, that single node in layer L? Well, that's just our nonlinearity that we're going to pass the score through, and it's going to be the score of that one single node in layer L. We're going to pass that score through the nonlinearity, and that's exactly what the output of that final layer is, the output layer. And so if we substitute for this, and we were to take the partial derivative of EW with respect to S1 superscript L, the score of that output node in the output layer, the else layer, big else layer, well, we're going to take the derivative of this squared error loss. Now, of course, this yn looks like a constant, and so this is going to wind up being a derivative of this nonlinearity because it's with respect to S. So if this output is the nonlinearity, we're going to pass that score through it. Well, if we take the derivative with respect to S1 superscript L, that's just going to be the derivative, the rate of change, the derivative of that nonlinearity theta. And so it just so happens for tangent, hyperbolic tangent, if you take the derivative of hyperbolic tangent of some quantity of the score, that's 1 minus tangent squared of that score. All right, so this is going to be something we're going to use when we define this delta function, and we're going to compute it through the tree for, in this case, the output node, but we're going to show what it looks like when you take the next layer down, beneath or before the output layer. And so in the layer before, this delta, we said delta was the partial derivative of the error with respect to the score of a particular node in a particular layer. Now, of course, with the output, that's delta j, that jth node, superscript L. In the previous layer, we're going to call it the ith node. So we say delta I superscript L minus 1 because it's the layer previous or prior to that. And we're going to expand that to partial derivative of the error of the output, or the error of the network, with respect to, that partial, with respect to the score of the ith node in layer L minus 1. And so if we look at the architecture of our network, here we have the output, that's EW, and we have the output for that node, jth node in layer L. And right before each one of these nodes is a score. It's the score of the jth node in layer L. And of course, from this, we take the partial of EW with respect to the score of the jth node, superscript L in the else layer, and we get this delta J superscript L. Now, of course, if we go to the layer below, we're now down here. And we want to compute this delta I superscript L. Now, of course, feeding into this L minus 1th layer is going to be the score of the ith node in layer L minus 1. And so what we want then for this partial, we're going to count what this output node, xi superscript L minus 1 for that previous layer, what it influences. Well, what does it influence? It influences the score for this node, the score for that node, score for that node, score for that node. And so in this, when we compute this delta sub I superscript L minus 1, we have to account for all of those components it influences in the forward direction. And so what we need then, if we're going to compute this chain rule for a path to go through layer L minus 1 to the other side where we get that score, we're going to have the partial of EW with respect to Sj superscript L. That concerns this nonlinearity that we take in layer L. And then we're going to have, by chain rule, that partial of the score for node J in layer L with respect to the input that feeds into these node J's in layer L. Now, of course, we're going to also have this partial of the input in layer L minus 1 for the ith node, the ith input node, layer L minus 1, with respect to its score for that ith node, layer L minus 1. And that's that last component. And so by chain rule, if we want the partial of the error with respect to the score for the ith node, layer L minus 1, we go through to the score for the jth node in layer L, and then from the score for the jth node layer L to the input that feeds into it, because it's dependent. You change that input, you're also going to change the score for the jth node in layer L. And then you have across that node that nonlinearity in layer L minus 1 for the ith node. So you have the partial of the output of node I, ith node, layer L minus 1, with respect to the score that feeds into that nonlinearity, the score for the ith node, layer L minus 1. Okay, so let's do a little bit of modification. If we take the first term, the partial of EW with respect to the score for node J in layer L, well, that's just our delta J superscript L. Right? That's what we got previously. And that quantity lives at each one of these J nodes in layer L. And we got that from the first round when we took that EW at the output. Right? We got that on the previous slide. All right, so that's just delta J superscript L. Now, of course, this next term, the partial Sj, with respect to the input I in layer L minus 1, well, again, it's with respect to xi. That means we have a constant here, w is a weight vector, and we have xi superscript L minus 1 to the 1 power. So that's just wij superscript L. That's just the weight vector. So we write wij superscript L. And so this last term then is the partial that relates, the partial derivative that relates the input for the ith node, layer L minus 1, to the score that feeds into that nonlinearity. If you change the score, you also change the output. What is that rate of change? It's the derivative of this score. So we write this nonlinearity theta prime of the score that feeds into the ith node, layer L minus 1. Okay, so now we have our delta J, and we're going to sum this across all nodes J, because this node in layer L minus 1, it impacts or feeds into, through the weight vector, each one of these node J's, J nodes in layer L. And so we have that sum. Why? Because this partial is impacted by all of these paths between each one of these nodes in layer L indexed by J and that ith node in layer L minus 1. And so if you're going to do this gradient is going to be impacted, this change, by each one of these pathways, each one of these weights. Okay, this influences multiple nodes J through each of these links wij superscript L. All right, so now if we take a look at this tangent, this nonlinearity, the derivative, well, we said before, the derivative of this hyperbolic tangent is 1 minus hyperbolic tangent squared of its parameter. And its parameter is the score at node xi in layer L minus 1. So we're going to write 1 minus our nonlinearity tanh squared of si superscript L minus 1. Now, of course, that does not involve j anywhere, so it's a constant. We can pull it out of the summation. And so we have our 1 minus tanh squared of the score node I, layer L minus 1. And we have our summation across all of the nodes j in layer L, wij, the weight vector, superscript L, times the delta j superscript L. So this is just a weighted sum of that delta function for each one of those nodes, along with the weight that feeds forward into that jth node in layer L from the ith node in layer L minus 1. So that's what this sum means. That's where that sum comes from. Now, of course, if we look at what tanh, our nonlinearity, tanh of si superscript L minus 1, what does that mean? Well, that's nothing more than xi superscript L minus 1. That's the same as the output of that node in layer L minus 1, which is the input to the j nodes in layer L. So we're going to rewrite this tanh squared as just being xi superscript L minus 1 quantity squared, because it's the same value. This is just the result of evaluating this score through that nonlinearity, or theta, or tanh. So now this is our expression for delta, the partial of error at the output with respect to the score in node I in layer L minus 1. And that's our expression. And so the interesting part is that when you compute this, well, you already have this output, xi superscript L minus 1, from the forward pass. Because recall, for the forward pass, you compute the weighted sum, get a score, compute the nonlinearity over that score, and you get the output. So from the forward pass, you already have that value that you're squaring. You already know what the weight vectors are. And then you have these deltas from the layer above. And in fact, once you compute the delta from the layer above, you send it backwards, or you so-called back-propagate it through the network to the layer below in order to compute the delta function, this delta, for the layer below. So that's why it's called the back-propagation algorithm. You're back-propagating these deltas, which are these partial derivatives of the error with respect to the score for the layer above. So you propagate these deltas back, and then you use that along with the x value, along with the weight, which you already know, and you use these from every node, the deltas, in order to compute the delta for the layer below. Hence the name backpropagation. You're backpropagating, coming down or backwards in the network from each one of these nodes j into the layer below. And then you're going to backpropagate again as you go down layer by layer by layer. Okay, so this is the backpropagation algorithm. And you start out, you initialize all of your weights at random, and it's important that they not be zeros. Because if they're zeros, if you think about it, weighted sum, some input times 0 is 0, and you're going to get 0 as an output. So you want to make sure they're not all 0, because that will give you poor initialization. But you go into a series of rounds, and you're going to then pick some n and compute in the forward pass, as it's called, all of the outputs for each node. In previous layer, going to the next layer, going to the next layer, going to the next layer, from the input, layer by layer, weighted sum, nonlinearity, output. Weighted sum, nonlinearity, output. Weighted sum, nonlinearity, output. And then finally, weighted sum, nonlinearity, single output. There's your h of x. And then, once you compute this forward pass, you have all the partial information you need for the backwards pass. You're going to compute these deltas starting at the highest layer in the network, layer L, going backwards, that delta. And then you're going to use those deltas and back-propagate them to get the deltas for the previous layer. So once you do this, you update your weight vector. Your weight vector is the old value is equal to the new value is equal to the old value minus your learning rate or your step size and times xi L minus 1 and the delta j. Now, if you wonder where this xi L minus 1 delta j comes from, if you look back at the network, the delta is this partial derivative of the error with respect to the score, right? So that's where that delta comes from, and the xi is just the partial of the score with respect to the weight vector. And so that's really just a decomposition of this chain rule here, right? This is going to give us our delta, this term, and this term is going to give us our xi L minus 1. And so we just multiply these together, and we use our step size, negate it, and we're using this gradient along the step, along the gradient, as what we use to update our weight vector directly in proportion to the error contributed or with respect to that particular weight. So that's where this expression comes from. And so here we update our weights in proportion to d e of w with respect to wij superscript L. So this is the eds portion, and this is the dw portion. All right. So you keep iterating again and again and again until it's time to stop. And then when you're done, you return the final version of your weight vector. Okay. So this is your back-propagation algorithm. And so when we have a neural network, we go in the forward direction, we compute our partial values that we need, and then we go in the backwards direction, computing our deltas, propagating them backwards through the network from a higher layer to its neighboring layer to the left, to a lower layer, and we update our weights through those products, the deltas times the x's. And so if you think about it, what this network is doing in the forward pass, we have a nonlinear transform, combination of values through nonlinear transform. These are essentially features. Feature is a nonlinear transform, like we talked about a phi function. But these particular features, they're tuned by the weight vectors that change, weights that change. These are learned features. And so you can't really interpret the hidden layers, but they are complexes of learned features that are increasingly aggregated, going from very simple combinations to combinations of those simple combinations. You can think of them as low-level features that are aggregated into high-level features and ultimately forming some hypothesis. Okay, so with that, that's all I had to say. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.